Thank you. Thank you very much. A fantastic Saturday. And thanks to all for joining at 10 a.m. for this workshop. And as Mr. Subhash Mandal, he mentioned, today is Netaji Subhash Chandra's birthday. Nationwide, it's being celebrated as Parakram Divas. So a great start this year. This is our first event from IEEE Bangalore section COMSOC. On 9th of January, we have had our AGM, and we also held our first ExeCom members meeting. We have 25 members overall, and that day we also had a follow-up of the AGM to our COMSOC ExeCom meeting. So let me express once more my sincere thanks to ExeCom volunteers, speakers who have made 2020 so successful year despite all challenges. In Bangalore section, recognized as outstanding chapter, large among the category. Also Global COMSOC, we were recognized as best chapter in APAC region. And we can see that through our workshops, and last year it was about 360 members associated with us. And then in 2019 end and 20 end, when you looked into it, 485 members. That's a significant growth that tells, the efforts that we are all putting together to take this communication agenda forward. There are many people joining, they're seeing benefits, and I'm sure many of you have joined as new members. So welcome if you have joined, and if you're planning to join, again, welcome for that too. I'm sure we will keep this spirit this year and achieve even more, not just awards and accolades, but as I said, truly championing the cause of communication society. And what can be better start? Today, we are starting this year's event with rural communications, how to use 5G and maybe beyond, but at least 5G is knocking at the door. This year, our academia, industry, startups, the way we have been working always, will all participate with full vigor to take on multiple streams. So if I have to categorize 4 streams, the way we're thinking 5G, last 2 years, we have talked quite a lot on the technology. We'll continue doing that, but time for deployment has come. And so we will talk this year even more on challenges on deployment, on operator issues, on spectrum. These are the topics that we will include for 5G's growth in global and in India as we start to launch trials and deployments in a broader sense. As we do this, we are opening a new stream. Sometimes it will be merged, but mentally we are structuring that beyond 5G, 6G. Most of the time, the previous generations, we as in India, have always caught up. It's a catching up game, and we have played our roles, but this time we want to play differently, and what better place than IEEE and Communication Society and Bangalore being hub for industries. We will start contributing significantly and have a conference, a flagship conference hosted on beyond 5G, 6G in few months' time. And then we will also continue some of the streams on its own right, like we have started intelligent transportation systems. There is ultra wideband technology coming, the blockchain, whether it is linked to 5G or 6G, but even otherwise, there are thoughts and newer technologies, and you do some little detailed hands-on kind of activities there. And the last stream, it's not just the technical. We know there is a big student community, young professionals. There are people in need. So software skills, patent papers, research methodology that we have been doing will pursue, again, those in full vigor. So with that note, I'm very happy to kickstart today's event on rural communication. We have 2 expert speakers. And Sandeep Agarwal is product owner from CDOT. Dr. Prasad Bhatt is founder and CTO of Astron. And what better kind of speakers we could have to talk on these topics. And yes, connectivity to rural, remote areas, to remove this digital divide in urban and rural sectors, it's very, very vital. We know 5G is for throughput, latency, and how this is pushing. But there are much more than that, whether it is last mile connectivity, whether it is licensed, unlicensed radio band, cost effectiveness, a converged architecture that is applicable for urban but can also take it forward to rural. There are multiple dimensions, and this workshop is all about that. So we will talk about technology, we'll touch upon certain deployments, and also about our Industry Connect program from IEEE. So those would be the focus of today's discussion. So thank you again for joining, and enjoy the rest of the 2 hours in listening and asking questions if you have. Thank you. Thank you very much. Over to Sudha.
Thanks a lot, Subhash. It's a very thanks for all the kind words, and also thanks for IEEE to host this talk and giving this opportunity to speak about rural connectivity, and also briefly about our product Gigamesh. So, as the context has been set, so we are talking about how technologies can be made to work for rural connectivity. So I'll be focusing on basically the delivery of the data to the end users from two aspects, both from the transport as well as from end distribution into the end users. So you may all ask that, okay, this transport and distribution also seems like some like electrical terminology, but yes, here also, since we are talking about spanning a larger geography, we have the transport and distribution being the access technology as a problem statement. So first I will talk about the core problem that we have in the rural connectivity. The first major aspect of that is the transport itself, which is how do you take capacity to the different geographies that we have. The primary problem here is that the area that you have in the rural sense and the area that you land area which is there for the urban is in a very, very skewed ratio. If you consider, for instance, Karnataka itself, Karnataka is a very big state where only 1% of that is just urban area. Whereas on a general note, the rural to urban area ratio is at the least 10:1. So that gives you an idea of how much area needs to be covered to actually provide the service in rural areas. So this is one major challenge. So the second major aspect of this challenge is that distribution. So if you, let's say, have a 5G or a 4G base station and you deploy that in urban versus you deploy that in rural, in the urban you will get a huge audience for that one tower. You will have hundreds of users, whereas in rural you may have just a couple of users for one tower. So it doesn't make sense to actually replicate the same infrastructure that is being done in urban verbatim in rural. So there has to be a different methodology to this. So in summary, the core problem can be put this way. So the number of users that are there in rural is small in pockets, but it is not so small also. The total volume is not small, which I will talk about a bit later. The number of users are concentrated in very small pockets and they are spaced very far apart. So that is a first major problem to solve. And the approach cannot be the same whatever has been done in urban. The second important thing is that the footprint of the access or the distribution technology cannot be the same again. So we need some other model. We cannot think of, let's say, for example, okay, if you want to address the same 100 users, let me put more power into the access. So it would be a gross waste of power, because access is usually like broadcasting kind of in terms of power. So you need much better schemes for it. And also we need better transport technologies to reach to the end locations. So in summary, the whole objective is coming to saying that we should deliver transport to as close as possible to the end user and have more localized distribution mechanisms. And why is it important to solve? I believe we are aware of this, but I would like to highlight a few more aspects in it. The first most important thing is that the rural population is very large. So this number I have derived it from Indian subcontinent, but the ratios are similar if you consider across the globe. The number of people in the rural areas is very high. Like we have 63% in India, and 37% reside in urban areas. So which means that that's a very literally two-thirds of the population is in the rural segment. The second major aspect is that the economy is best if it is decentralized and you are able to, let's say, address different applications in rural areas. So for that, one of the primary backbone is data communication. And also there are several cases where remote factories become very feasible if connectivity is reached. Factories are a use case for different industries, both from the point of view of cost as well as from the point of view of say deployment requirements. All of that, the remote factories are best done in rural areas. So those are that becomes feasible if you have the data backbone. And last but not the least, the most important sector which is underperforming in India is the agribusiness, and having a backbone of data plane will make that agribusiness boost a lot. So the logistics problem that is felt by rural can be split into two parts. One is the data transport and the other is the physical goods transport. So by the rural technologies that I'll be talking about, we need to at least address the first problem. The second one will follow through that. So from the point of view of transport technologies, there are multiple choices. We are all aware of the optical fiber-based communication technology. It's very established. There is, since about 2 decades, there have been technologies which are related to FSO, which is free space optics, which are being deployed, even though there are problems, but that is a choice. Fixed wireless is another choice. By fixed wireless, I mean using, let's say, Wi-Fi bands, 2.4 or 5 gigahertz, or even the 3G, 4G, 5G kind of bands. fixed wireless is one option. TV white space is another option, which was, I would say, most talked about in the last several years. There are problems, but that is still a viable option. Then V band, E band, P2P wireless. That's another big option where you have the very high bandwidth available at higher frequency band. And GigaMesh, which is a product that Astrom has. So that is one more option. It is not point to point. I will talk about that a bit later. One particular segment which I have not specifically mentioned here, but I would like to orally communicate, is a SATCOM. SATCOM is also a choice for transport. I will touch upon that in the later half when I talk about a use case and say what needs to change in SATCOM if it has to become a viable alternative. So now coming to the first one, the optical fiber-based communication, we all are aware that it can bring very, very high capacity in a concentrated way. And it has been the baseline technology for several networks. And if we consider the current operating internet, the global internet is running on fiber. So that is a very fundamental thing to consider. And you don't have any of these spectrum issues that the wireless devices undergo. And it can give you really, really long range. But it comes with its own baggage of problems. The capex is very high, extremely high. So unless the high capacity and the requirement offsets it, the capex will be the major blocking factor for optical. And right-of-way is another major problem, especially in cities as well as in rural areas, because you need to literally dig trenches, or you use, I think, some innovative mechanisms like putting over the poles. Still, all of that said and done, the right-of-way is a bigger problem. And the next major aspect of that is that the time it takes for deployment installation is significant. And if we consider the last mile has a lot of maintenance issues. Pardon the spelling there. It has a lot of maintenance issues because especially in developing economies where you would always have some, say, parallel work going on, some, say, let's say in case of Bangalore, you will have BWSs be digging up trenches here and there for obvious growth related reasons, and then something getting chopped off, and then you lose the SLA, and then you have to restore it. So the last mile, I would not say the backbone, but the last mile is a very critical problem for optical fiber. So the technology is well known, so I don't have to talk about it. So let's move on to the next technology, which is a free space optics or optical communication. Now this is a relatively new technology, but it has failed to pick up. I will talk about what all things have happened in that. So the first major thing is that this is a technology where you are using the infrared spectrum and you are creating very pointed infrared beams from one node to another node. And for instance, the picture that you see here, the array of these small ones on the right side and the left side, these are the transmitter array of 8 of them, and the central one is the receiver section. So this is one particular case which was available in public literature. There are many variants there. But the basic thing is that this is basically using the infrared spectrum to establish a pencil, in fact, even finer than pencil kind of beams from one node to another node. The advantage of infrared spectrum is that the bandwidth that you'll get is phenomenal. So you can do 1020 Gbps, that is possible. But the infrared spectrum, as we are aware of, it gets easily blocked if you just have some medium fog cover, and if you have rain also, it breaks. So it comes with high capacity. The right-of-way is very simple because it's wireless in effect. So you just need 2 points to be deployed. And there are no spectrum issues here. So there is no question of spectrum allocation or problems related to that. And but it comes with very high maintenance. Deployment requirements are very stringent because the alignment between the nodes has to be very precise. So the deployment effort is very significant in terms of alignment. The maintenance is high because of the same reason. The beam has to be very precise. So if there is a small offset, it degrades immediately. The capex is relatively high compared to so many other wireless technologies, and the SLA is not so great. Of course, it also requires line of sight. So these are the basic weighing factors for and against free space optics. Now coming to fixed wireless, which is another popular choice, I would say, for rural kind of transports. It's a known technology which has been upscaled for a longer range, and it can operate for medium to long range. And it can work very effectively for non-line of sight. So line of sight is not a requirement, but it would help. It is not a requirement. And the cost is very low compared to fiber-based deployments. But the primary factor which weighs against fixed wireless is the capacity that you get, the bandwidth that you have, and the capacity bitrate that you can realize with that is low. And it also has very high interference because all of these bands, whether it is a 0.9 gigahertz, which is currently used in India for 3G, 1.8, which is used for 4G, 2.4, which is used in all our phones and Wi-Fi modems, even Bluetooth for that matter, and 5 gigahertz, which is used for basically the localized Wi-Fi. So all of these are potential sources of interferences for this to work. So that causes a lot of problem in terms of performance. So even if, let's say, it was in ideal condition giving you a certain bandwidth, if you introduce some interference, the bandwidth will drop dramatically. So this is one of the primary disadvantages that fixed wireless has it. The next technology of interest is TV white space. So in fact, there are several even say products which came out very rapidly in the last, I would say, 3-4 years, primarily because the TV space, TV white space, or rather the space that is there between the TV segments started becoming more attractive for communication. And in turn, also one more thing happened, the TV concept of using the terrestrial regular frequency band itself diminished. It got replaced with either DTH, SATCOM based, which uses KU band and KA band, or it became replaced with the regular internet itself with on-demand television. So the TV white space became more bigger and bigger. So, and that falls roughly in this band of 470 megahertz to 700 megahertz. It's a very lucrative band because it gives you very low loss and it has very good bending properties, non-line of sight. So those are all very great things, and it also gives you very long range compared to let's say even the band of related to the fixed wireless. This gives you a much longer range, and the instrumentation cost is very low. The technology is also quite known. With certain modifications, it's able to give the necessary power as well. The disadvantages that come to its place, one is low capacity, and the other one, in Indian context especially, I think the spectrum licensing has become one issue. It is not yet sorted, I believe. I think the Doordarshan needs they need to still relinquish, and so many problems are there related to that yet. So talking about the next, I would say, leap in technology, it's the V band, which is 60 gigahertz range. Of course, the V band extends all the way from 40 to 75 gigahertz. There are different bands which are allotted for different purposes. 60 gigahertz is something which is called as unlicensed band, extremely popular for say point-to-point and even indoor applications. In fact, there is an IEEE standard, I would say, a subsegment of 802.11, which talks exclusively of V-band based Wi-Fi routers, indoor Wi-Fi routers called as WiGig standard. So that is one important application in indoor environment. But people have actually also made equipments which can be used for outdoor versions. However, the 60 gigahertz inherently has one problem. The oxygen molecules in the atmosphere absorb this very, very effectively. So it actually corresponds to the resonance in the oxygen molecule. So it matches that band very well. So whatever, I mean, if there is air, if you are trying to pass this signal through air, it attenuates very, very badly. So that is one deficiency of this. So I will not be specifically looking at this as an alternative for transport for rural, because this would absorb very heavily. So the range, I mean, on a typical node, will be like 200 meters, and some people have claimed to reach about 1 to 1.5 kilometers, but with very low SLAs. So this is a very lucrative band, and I think this is going to take off in terms of indoor, or let's say very localized, even access technology. So now coming to the next higher band from the 60 gigahertz, E-band. E-band is actually starting from 71 gigahertz to 76 gigahertz, and then 81 to 86. There's also a segment in the 90 gigahertz, but that is also taken by military, so there's that is less and less used. But 70 gigahertz and 80 gigahertz, these 5 gigahertz slots is very large and very efficient, I would say, in terms of the range performance. So this is a very, very attractive band. And the additional thing that has happened globally in several segments is that this band is also something called as light licensed, in the sense that if you realize, let's say, a 1 degree beam with these kinds of antennas, you can reuse the exact same band for different links in the same geography. If you contrast that with, let's say, 3G, 4G, 5G antennas, they all have very wide bands going to like 30 degrees at the least, going to like 60, 70 degrees at the max. So sectoral antennas. So if a particular antenna is using a particular slice of the bandwidth, you cannot use the same for another antenna in that same geography in those bands. Whereas here you can, because the beam width is very tiny, very narrow, it's coming to about a degree. So you can easily place multiple devices as long as it is not in the exact same pathway or in between the two nodes, you can reuse this band. So that's a very positive thing about E-band. And the capacity that you get is very high. SLA is very good compared to, let's say, FSO kind of bands. Of course, if you consider lower bands, the SLA is slightly worse off because of rain attenuation, primarily rain attenuation for P2P radios. However, that gets offset by the fact that you have a very narrow beam, so the antenna gain is very large. And it's easier to also get that antenna gain of 1 degree. Just talking about it a bit more, let's say the antenna footprint will be like about 30 centimeters to get 1 degree beam width in E-band. Whereas if you want to get that 1 degree in, let's say, lower bands, let's say KU band, you would need easily something like 80 centimeter to a meter, somewhere of that order, to reach that kind of 1 degree beam width. So that's a physical advantage that the band gives you because of the frequency being high or the wavelength being very short. However, the current P2P radios have one problem, which is the capex is very high, and the link that is formed, the 1 degree beam that is formed, is mechanically created using a reflector. So if there is any problem, any misalignment, the only way you can fix that is that you go to the site and you align it. So that's one disadvantage. And as we go to higher frequency bands, almost like above going up, I mean, into the V band and further on into E band, the line of sight becomes a requirement in terms of link establishment. However, you could always look at repeater-based architectures to cover up that particular deficiency. The capacities that you can look at here is of the order of even 10 Gbps. People have achieved that in the short range. And 2 Gbps, to be frank, it can go even up to a 10 kilometer range, 2 Gbps. And it's ideal for, let's say, 5G kind of backhauls, because this gives you that kind of capacity that you need for both urban and rural settings. Now comes the GigaMesh product. So here I introduced this product called as GigaMesh, which Astrom has developed. So here this is giving you very high wireless capacity, just like any other E-band radio. But in addition, so we have done one additional innovation in the hardware design. So this is an array-based design. So all of the beam formation, which is the 1 degree beam formation, is purely electronic here, and also driven all the way in the digital domain. So that gives an advantage of being able to steer the beam and form the link in a remote sense. So there is no need for, let's say, deployment onto the site for any link alignment. So that is that actually reduces the OpEx cost, as well as in deployment sense, the deployment related effort is much lower. The capex is also lower for an additional benefit. So this box can create multiple point-to-point links from one device itself. So all of the existing E-band devices talk about basically, if you want to establish one link, you need 2 devices. So you just make a pair and then establish one link. Whereas here, one device can form up to 6 links. So you could have, let's say, an architecture where there's one device, and then at the edges you have 6 devices, and they all establish the link. And the edge nodes again could be establishing multiple links to some other device. So it allows for basically meshing topologies. So that actually brings in more capacity as well as redundancy into the system. So that as well drops the capex. And long range is possible because the inherent power that we are realizing because of our digital beamforming structure is much higher. In fact, the lower end of the configuration that we have meets the higher end of the E-band P2P devices that are there in the market. So the higher end of this gives you a very long range. And we are working towards integrating the DU and CU, distributed unit and central unit architecture of the 5G into the box itself as hardware as well as firmware, so that the effective deployment requirement on the site reduces to one box. One box just for all the access and all the computing resources, and then you can have RU radio units for the 5G deployed attached to it. So so the primary part to summarize in GigaMesh sense is that this is having very large bandwidth to begin with, E-band, that gives that, and the capex and opex are being reduced because of multiple beams being formed, and it is scalable to very high capacity. Easily we can go to 100 Gbps kind of capacity by just doing a configuration which is like 360 configuration, and it is suitable both for short range and long range, and it's a modular design, so it can be easily scaled that way. And it's a 5G ready design. So we talked about different technologies so far in terms of transport, all the way from fiber to different wireless technologies. And I'll just quickly touch upon the technology choices that are there for access. So as we discussed in the beginning, the distribution mechanism or the access mechanism has to be more localized for rural. We cannot expect to have a very high power, large range one access device, so that doesn't work out as such, both for the sense of coverage, power, as well as in terms of capacity. It is either it will be either over designed or it will underperform. So one of the two will happen. So that's why the distribution mechanism has to be very localized. So for instance, a Pico or a femto cell concept will work out very well from 5G or 4G sense. And that model can work very well where it just covers, let's say, one village. which will span hardly about, let's say, 200, 300 meters to maximum half kilometer. So it will be almost like 1 lane or 2 lanes will make up a village. So it will just cover that area. That much coverage is just enough with just one antenna, perhaps. And Wi-Fi is another model where you could just use a hotspot kind of architecture, which could operate in either the traditional 2.4 or 5 gigahertz, or it can go into the Wi-Gig band of 60 gigahertz for that particular localized spot. The other mechanism where for, let's say, factories and other deployments could also be a local area network there, which could be then terminated into wired or wireless further devices. So this could be the localized mechanism to solve the local distribution problem, instead of a much bigger, let's say, tower-based deployment in terms of the 4G, 5G antennas. A more compact form of pico-femto kind of cells is the right choice for access. So I'll now talk about one particular use case that we sort of went through, putting together all of these transport technologies and seeing how they perform for a use case. For the use case, we picked up an area which is near Mysore. So this is an area shown from Google Earth. So this is an area which is starting from Mysore's the optical link terminal, which is literally near the center of Mysore, to two other OLTs, Nanjangud and Fulali. And this is an area which covers about 5 towns and 33 villages and about 40,000 households. So we took this as a use case, and then we looked at different technologies, how they can be laid into it, and what would be the implication in terms of cost, deployment, and all of those. So first, let's start with the OFC. So in the optical fiber sense, we already know that these 3 points have an optical fiber backbone termination coming from BharatNet project. So all of these pink nodes, reddish pink nodes, are the ones which are the additional nodes that would have to be deployed, and these white lines are the additional optical fibers that would have to be laid out. So this is the kind of deployment which will cover all of those villages as well as the towns that was listed in the previous diagram, and this would be enough to do the transport. And additionally, there can be an agnostic access device, which can be either the 4G, 5G, femtocell as discussed, or the Wi-Fi or the LAN, that can be worked out on a local sense. The next one is basically free space optics as a deployment. So that is also a line of sight kind of architecture. You can see that kind of design there. So this covers similarly, where all the green nodes are basically the new FSO nodes. You would obviously have paired FSO nodes on the main centers. So each one has a pair. It's a pair-based architecture. So this is the deployment strategy that we had worked out. Moving on to the next, fixed wireless. The beam width that you get in fixed wireless is sectoral in nature, a very narrow sector. So for instance, one particular case that we had looked at had a sector of something like 8 to 10 degrees. So that is one option. So for instance, here you can see that there are 4 such sectored antennas that are deployed from this OLT, which covers this area, and then different from here. So all of this primarily to just cover all the villages that are present. So that kind of deployment that we had worked out. So there are some cases which we could not cover. I think there is one spot or so because of the reach as well as the kind of the localized problem there. But mostly it covers everything. And the other case, which is the TV white space case, is similar. The sector beam width again changes there. It can be 8 to 10 degrees also. There are some products which even give something like 33 degrees. So those are the different choices. We have considered one of them, and then that layout will be somewhat similar. Moving to the next one, which is the E-band P2P. I have excluded V-band because it is not suitable for the range that is required here. Here in E-band, you have again point-to-point radios. Each one is one point-to-point. So each link expects a pair radio. And this is the kind of architecture with which you could achieve the necessary linkage. Remember that this is also cascading. So for instance, from here, the data will flow to this and to this and to this point and to this point. So that kind of cascading is worked out here to optimize the deployment architecture. And also we looked at GigaMesh as a deployment architecture. So here the primary change comes into the fact that in a particular sector, for instance, the nodes like GMC 90, this is one configuration which gives 90-degree field of view. For instance, these three links, all these three links will be formed with just one box. Here also this can form in one box. Whereas if it is falling outside the 90 degrees, then there will be one additional 1 unit box. So we have considered cases where it is a narrow field of view, wide field of view, and optimize this particular deployment again. So this covers literally all of the requirements here. So with all of that study put together, so we worked out what is the capex needed to achieve each link. What is the capex when it is factored down to per Mbps that is delivered per link, and how much is the capex per Mbps if it is factored down to covering 1 square kilometer area. So we looked at all of the different cases, we put them together in terms of cost. So one very easy to look at, one easy to see case is the fiber. The cost of fiber is phenomenally high, both in terms of per link cost and per Mbps cost, as well as per Mbps per square kilometer. So there are, I'll talk about the other ones also. If you look at FSO is considerably lesser. It comes with lower SLA, just to point out, compared to fiber also. But this one is still better off compared to fiber in terms of the overall cost. It is not so better off compared to all other wireless technologies. So if you look at fixed wireless, TV white space, they roughly fall in similar buckets. And E-band, the P2P devices fall in one bracket, whereas GigaMesh falls in another bracket. So GigaMesh is roughly, if you consider per link cost, is comparable to fixed wireless TV white space. So they fall in one bucket if you just look at the per link cost. But if you look at per Mbps per link, so if you factor down to saying that, okay, if you want to deliver a certain rate expectation, how much is the capex that you would incur? Then the TV white space and fixed wireless obviously shoot up because they come with lower bandwidth to begin with. FSO is slightly better than them. But the E-band P2P as well as the GigaMesh devices are better compared to others when it comes to higher capacity. So this is just to say that if a particular geography does not require much capacity, let's say the village density is very, very low, then those, or the overall capacity requirement itself is very low, then yes, the fixed wireless TV white space are good options. They're not at all bad. But if you want to pump in more and more capacity to a particular area, then these don't fare very well in terms of cost. Whereas E-band fares better there because inherently it comes with higher capacity. And if you look at per square kilometer per Mbps, again, you could see that the fixed wireless TV white space is not faring so great. In fact, some of them could shoot up as high as even fiber in terms of per Mbps per square kilometer, that metric. And the E-band devices are much better, even the P2P devices. The primary thing this is pointing out is saying that the capex, if you go to the higher frequency bands in terms of millimeter wave, the V band, E band, the cost comes down dramatically because you can pump in more data. So ultimately, the transport problem comes down to the fact that how much can you give more for lowest cost. So in terms of the capacity as a pipe capacity. So higher you give for lower the cost, basically the these factors come down dramatically. Even though this here it may be comparable to all other technologies, but the link capacity will be the one which will ultimately start not faring better for the lower bands. So that's an important metric to remember. So the reason why this is also important is that we have to remember that the rural audience, even though they may be distributed in their positioning, it doesn't mean that they are not data hungry. Everybody wants to watch videos. Everybody wants to generate content. So rural audience is no less tech savvy than urban audience. It is just that they are distributed. So that is the harder problem to solve. Not the fact that there is no demand. The demand is phenomenally there, especially with the penetration of all the smartphones. So there is literally, I mean, in all the villages that I am associated with, I don't see anybody having any feature phones anymore. Everybody has, even if they have feature phone, they will definitely have a smartphone on the side, saying that okay, they'll make calls from this and then they'll use that. All of that optimization they do, but they will always have one smartphone with them. The unfortunate problem is that they don't get the capacity there to actually utilize the strength of the smartphone. So that's where the all of these technologies can bridge that particular thing. So we have put together some basic parameters that we had used for the study. And we have considered, I've also explained the reason why the fixed Wi-Fi, wireless and the TV white space has higher cost per Mbps because of their lower capacity. And the per link cost of fiber is calculated based on the distance, basically, what is there between the different deployment that we had considered. At this point, I would like to also bring in one other part, which is not really in the slides, but I would like to bring it up, which is related to SATCOM. So if you look at the revolutions that are happening in the SATCOM industry, like for example, the Starlink constellation that is coming up, or the OneWeb, which sort of became, went up in fame in 15, 16, 17, but then had a financial crunch, and then Bharti came, took over with UK government. All of that happened. So basically that sector is undergoing a lot of transformations. The primary problem that they still have is that the capex that is being incurred when you are using lower bands. Again, the bands of interest are KU band and in some time KA band and also V band. So that they are slowly moving upwards. The KU-KA band inherently comes with a very large capex. So that capex is something which will basically cost them in terms of realization. There again, going to higher bands of V band and E band makes a lot of sense in terms of reducing the capex, because the capacity that you get, the bandwidth that you get is very high. And in KU-KA band, they are literally working to get the necessary, even the power, the EIRP that they need to establish the link very well and then transport very well. Of course, the tests are going very nice, very good, but when it comes to the final realization, they need to work in tandem with all the DTH providers who have certain transmissions already happening in KU-KA band, and these should not interfere with that. So all of that puts in a lot of restrictions in terms of how much is the capacity that they can realize, and hence the capex cost per Mbps goes higher. So in fact, that comes to a closer or slightly higher than the fiber. So that's where the ballpark comes in right now. Even in the Starlink constellation that is being deployed. So unless there is an optimization done there and they move to higher bands, this capex will not be very competitive compared to other technologies. So just to give you a background, at Astrom we had worked on a satellite constellation which we have sort of deferred for a couple of years now to work till we finish and deploy gigamesh successfully in different geographies. So there we had basically explored using E-band as the primary band for doing all the internet delivery from low Earth orbit. So there we could see that that would bring down the factor of Mbps cost by easily 1/8 to 1/10. So that is which will put roughly in the league of these, the other E-band P2B, which is important for its rapid adoption in rural markets or any markets for that matter. So I think that sort of puts together all the different points that I wanted to say. I'll just quickly point over the future scope of what is being discussed here. The study is done to some level, but there is much more in-depth, I would say, digging to be done, work to be done. So Astrom is part of TSTSI and there we have been doing a study on rural backhaul with focus on using technologies like E-band frequency for achieving it. The study number is in NIP258, and we are working alongside with C. Sutta, Sankhya Labs, Reliance Jio, IITM, the IITM's 5G unit, and SEVIT, as well as Tejas Networks, to basically do a much more in-depth study and take this activity even more deeper and further into the realization plan. And also, one of my colleagues here at IEEE was mentioning about IEEE 2061, which is about frugal 5G, where they were looking at a similar aspect of using wireless mid-haul, basically to reach this kind of objectives. I believe the discussion that I'm doing is roughly going in that kind of directions. So that would be one sort of an alignment point that could be considered further on. So these are the different pathways ahead for the work that has happened in terms of rural connectivity that I explained. And that's it. I had to say thank you. Thanks all. If there are any questions, I'm open for it. Yes. Great. Thank you.
Yeah, thank you. Thank you, Swal sir. So is my slide visible? Is my slide visible? Okay, thank you. So hello everyone. I'm Sandeep Agrawal, affiliated with Center for Development of Telematics. So today's presentation would be on rural communication, and I'll be discussing on the Industry Connect program, which we have initiated as part of IEEE SA, as well as some of the works what we are doing in CDOT with respect to rural communication. And also we will look into the present requirement of connecting 600,000 villages in India, mostly from Gram Panchayat to village level connectivity. So I'll try to discuss those aspects as well. So agenda of today's discussion, first will be overview of rural communication with objective, deliverable, engagement, and related work which is going on right now in IEEE. Rural connectivity challenges, which Prasad has anyway articulated in his presentation. The rural broadband architecture, which we have proposed and which we are working right now, along with some of the product which we have developed at CDOT, and also connecting 6,000 villages in India. So we have we studied along with policy group of NTI PRET. So I'll present the data what we have collected from there. So objective of Rural Communication Industry Connect program focuses on providing meaningful connectivity by improving the communication infrastructure in rural area that can improve quality of lives of the people inhabiting in those areas. The goal of the program is to contribute towards the goal of global, including rural community digital inclusion, by developing solution for rural and remote area using suitable technology. So this Industry Connect program recently we have started, which got approved by IEEE. So the idea is, to study what type of rural initiative being taken globally, and what type of solutions people are deploying to meet the connectivity requirement in their area, and to learn from their experience, understand the gaps which are there, because Industry Connect program is actually a pre-standardization program through which multiple gaps can be identified and multiple standard groups can be created to actually address those gaps. So deliverable, what we are looking from the program is basically identifying the broadband requirement in rural community, identifying the gaps in existing standards, submit new standard project proposal. The group together, or the individuals, after identifying the gaps, can submit new proposals to IEEE through the standardization mechanism. Recommended practice documents, workshops and events, webinar, white paper and report. These are the some of the deliverable what we are targeting as part of the Industry Connect program. With respect to engagement, as we all know, the rural communication is something which has been talked about every time whenever there is a new technology or the telecommunication technology coming up, because somehow the gap is reduced. The connectivity in the rural area has definitely improved, but still if we go by the global statistics, there is yet to be done, lot to be done to actually provide we say meaningful connectivity to the people, so that with the connectivity they will be able to perform some of their day-to-day activity with ease, and it really helps in either improving their life standard, or improving their income, or helping them do work more efficiently, and even in a reduced time with reduced hardship. So for that purpose, we will be looking to engage with industry, academia. There are lots of NGOs and INGOs which are working in this particular area. So we would like to, engage with them, hear from them, and understand how they are solving the problem today. Local, municipal, national government authority working on developing communication technology for rural areas, and collaboration with rural test bed, because this is something which has was not a real focus before 5G, but when the 5G is around, there is lots of talk regarding the test bed, which will help provide innovative solution. So there are multiple test bed we understand already active, some in Brazil, some in UK, which are specifically focusing on rural communication requirement. Even in India also, there are certain test bed which we understand are focusing some of the use case very applicable for rural area, like financial transactions. How to increase financial transaction in rural area through technology, and especially 5G technology. So we want to collaborate with them as well to perform multiple pilots as part of the program, and looking for multiple active participation from Asia, Africa, Latin America, and we are already discussing with some of the folks in these region to come on platform, discuss, and we understand from what they are doing, and they understand from the technology what we are deploying. So related work which is right now undergoing in IEEE is one of the work which we are driving is interoperable and secure wireless local area network infrastructure and architecture. It is also called is a WANI P2872. So the focus is to develop a public Wi-Fi architecture which is not only suitable for urban and semi-urban area where there is a higher footfall of the people, but also to the rural area, so that the rural people can also get benefited through the public Wi-Fi infrastructure. Another thing, as Prasad has also mentioned, so there is Frugal 5G P2061 group where we are working to define architecture for low mobility and energy efficient network for affordable broadband. So I'm working as a vice chair there, and there is lots of activity going on with respect to mapping the rural requirement with frugal way of deploying some technologies, as well as now recent discussion is going towards unified 5G core for rural as well as urban requirement. IEEE 802.11 Wi-Fi is something which is considered as one of the most prominent technology to provide connectivity in rural area as well as urban enterprise, in-home and all other places. There is another program that is DITA, that is Digital Identity Inclusion Trust and Agency. Apart from that, there is IEEE INGR CTU, that is connecting the connected working group under IEEE Future Network Initiative. There also the vision for immediate 5 years, 10 years vision for how to increase the connectivity in rural area is being discussed. And apart from that, another work which is driven by India is 1941.1, where internet grade of services are being defined. So in rural area, if there are multiple services being used by end user, what could be the grade of internet in terms of how much bandwidth those applications require, and how much QoS can be defined, which can be used by ISP, TSP as a recommended practice document to deploy the network. Also, there is a similar work which is going in TSDSI, that is Telecommunication Standard Development Society of India, where the group is working towards developing and reference architecture for rural broadband. So there is the work has just started, so it is a good platform for anyone to contribute with their expertise and the research what they are doing. I'll just go through two main projects, that is P2872 and P2061, to give an idea that what is being done in those groups which directly complement the rural communication requirement. So in P2872, basic idea of developing interoperable and secure public WLAN network infrastructure to provide seamless connectivity of users. The network infrastructure shall consist of Wi-Fi access point of different makes or models from different vendor. Backhaul connectivity provided by different service provider. Authentication policy infrastructure services offered by different application service provider through subscription plan. So the whole idea of this particular standard is to unbundle all the players in the ecosystem and provide them framework so that they all can coexist and interwork with them each other on defined communication APIs. And this particular work is mapped with respect to our ambition in India to deploy around 10 million Wi-Fi hotspot by 2022. So when we have such ambition of having each nook and corner of the country with public Wi-Fi, the architecture should support all type of users, all type of device, all type of heterogeneous Wi-Fi network deployment, multiple players like TSP, ISP, small entrepreneur, and all other, so that they all can coexist and provide services to the end user as well as make business out of it. So if you see, recently on 9th of December, Government of India has approved a public Wi-Fi framework called PM WANI, that is Prime Minister's Wi-Fi Access Network Interface Framework. So this particular work directly complement the framework which we will be deploying in India to provide affordable broadband through public Wi-Fi network. So as part of P2872, we are looking at each player of this particular ecosystem. If you see, there are users who are one of the biggest stakeholder in the whole ecosystem. And now user profile, if you see, there are users in urban area, users in rural area, users in an area with no cellular coverage, user in area with only Wi-Fi coverage. Their usage pattern is quite different from urban to rural, and there are multiple onboarding mechanisms which user has to go through to access the service. Similarly, devices, now again there are multiple type of devices which we see in the network, like only Wi-Fi supported, Wi-Fi for cellular, old and legacy devices, new devices which really support SIM type of authentication. Now there are devices which doesn't have any interface to input any data, like sensors or surveillance devices. And now going forward, we will find multiple connected devices which will also going to utilize the infrastructure. Similarly, there are Wi-Fi network which has multiple variant. There are many players like TSP, ISP, aggregator, neutral host, app provider, roaming hub provider, and public security infrastructure provider. So these all players also has to coexist and work with each other in the network. Similarly, we see when there is such infrastructure deployed to meet both urban and rural requirement, there are multiple agencies which are also a stakeholder in this particular network. Like lawful agencies are one of the biggest stakeholder in such network. A smart city authority, government state agency, data analytics agencies, disaster authorities, these are also a stakeholder and they should also coexist in the network. And there should be a provision for them to have data, or they can send the data to the end user through such public network. There are multiple applications as which users are going to use. Multiple deployment scenarios are there, and multiple plans are there which user has to consume, free or paid or multiple programs. So as part of P2872, we are looking into each of this aspect, identifying the gaps, and then migrating the architecture to meet a public Wi-Fi requirement which is suitable for both urban and semi-urban as well as rural deployment. So coming back to another initiative with respect to the same communication is now Frugal 5G network, IEEE P2061. So this particular architecture is, looking at multiple aspects of rural connectivity, like the affordability for the end user, that whether the internet or data plan what he's purchasing is affordable as per his income level and his saving. Local content generation and storage, because the architecture should also allow hosting of the content at the edge node, so that access of the content is easy, as well as there is a mechanism to even generate the local content and then distribute the content over the network. Connectivity in the remote areas, manageability of the network, because once it is a rural area, the manageability of the network is very important, because it is also associated with how much uptime of the network is, as well as reducing the OPEX cost of the network. The Frugal 5G also looks at limited mobility, because in rural areas the mobility is pedestrian level of mobility is predominant, and mobility of vehicular type mobility is very less. And vehicular type of mobility is more on the road, but within village the mobility is more of a pedestrian average mobility. So the architecture doesn't need the specification which meet maybe 200 kilometer per hour or 500 kilometer per hour mobility requirement. So the architecture focuses on the technology which can meet the average mobility requirement of the rural area. Localized communication, that if people want to communicate with each other or between the cluster of the villages, they may not require to connect to the national grid for all such communication. Renewable energy, because energy or the power availability in the area is also one of the challenge. And cluster service provision, because the population in rural areas are sparsely populated, so how cluster based connectivity can be provided. So these all become part of Frugal 5G requirement, where the work is presently undergoing. With network architecture perspective, as Prasad also mentioned, so we are looking at access, middle mile. These are the two major component. So basically the middle mile is where we are looking at microwave type of communication to from the center node. The connectivity can be extended to the nearby villages either using TV white space or fixed Wi-Fi. And going forward, we will also discuss about E-band and other technology to meet the middle mile requirement. So if you see the diagram here, the central fiber pop, if we take example or analogy in India, so Gram Panchayat is where the fiber pop is terminating. On the fiber pop, there could be a micro base station to provide the nearby connectivity. And from micro base station, the nearby villages, which could be 2 kilometer, 3 kilometer, 4 kilometer, 5 kilometer, a fixed point-to-point connectivity can be extended, and that connectivity can be distributed using Wi-Fi hotspot or even through a fiber or copper line. So this is how the village cluster will be connected, and there will be a a fog mechanism which will help to achieve multiple local connectivity, like local communication between these clusters or sharing of the content among these users in the cluster. So those aspects will be met by local fog which will be maintained at the central location. So large coverage area cell to provide ubiquitous connectivity. Small cell like Wi-Fi hotspot as high-speed access point connectivity in the clusters. Wireless middle mile network to backhaul the data from the central location to the nearby village location. and those middle mile network could be point-to-point wireless link to connect the nodes in the villages. So this is the present work what is going on, along with multiple other discussion in P2061, and the new discussion what has started is more on a unified core 5G core for both rural and urban requirement. So that work is going on. So I highly recommend anyone to connect to those calls and contribute. So apart from that, now talking about rural challenges, which are multiple time it has been defined and discussed, and the challenges are not changing actually. It is low population density, sparse and clustered population, remote and difficult area to access, comparatively low income level. One thing which generally we don't listen quite often is how to solve requirement of lack of education and exposure to absorb digital technology, because the end user may not be educated or digitally aware to use digital technology in the area. Then how human computer interface can be designed to enable such digitally illiterate population to absorb the digital technology. So that is also one of the major requirement in rural area. Apart from that, inadequate grid power supply, inadequate backhaul bandwidth, price benefit comparison with urban suburban areas are major challenges in rural area. So rural broadband architecture, if we discuss, then we have seen access, middle mile and backhaul are something which is always required, because in rural area your point of presence or backhaul point of presence will terminate at some location, and the area where the connectivity required to be provided is maybe 2, 5, 10 kilometer away from there. So with respect to access, something which user will directly connect to, that could be Wi-Fi hotspot, or that could be cellular base station. And then apart from there, to connect to the actual fiber backhaul or where the internet connectivity is coming, there could be a wireless connectivity, maybe in 5 gigahertz or TV whitespace type of sub gigahertz connectivity. Or if these aspects are not there, these technologies are not there, if satellite is is only possible connectivity there, then satellite works as a direct backhaul where we may not require a middle mile connectivity at all. So once internet bandwidth is extended to the end location, we understand that only making connectivity available may not serve the purpose of rural connectivity. So apart from access, middle mile, backhaul technology, rural broadband architecture also require local content in regional language. So there should be a mechanism or a technical support to have local content acquisition, generation, and distribution. Voice calling facility, that people may want to call themselves, or they might want to call to someone connected to the national grid, or they want to call among the cluster of the villages. So such type of local VoIP server is required to be installed to facilitate such type of communication. Another one important aspect of having affordable and sustainable business in the village is a mechanism for voucher-based low denomination access for affordable internet. So there require a mechanism where certain village level entrepreneur can start an internet reselling business out of the connectivity which is made available there. So there you require certain box which will facilitate such type of internet reselling in the area. Support all type of access devices, support for emergency alert notification to the people, and rural specific network slice can be facilitated to have let's suppose free access for frequently used content or something which is very important to that area. And the premium content can be charged where people want to access high bandwidth content. So that could be, premium content, and some could be a free content. So such type of architecture can be, designed to meet rural requirement. Rural connectivity solution from technology perspective, what CDOT has developed. So I'll just, quickly go through these solutions. So one of the product which we have designed, which will help, any entrepreneur to resell the internet in the area and provide affordable broadband to the end user, and also make business for his, need, is called public data office, PDO. So this is the same concept of earlier year PCO, where an entrepreneur used to set up a PCO booth, and from there the end user get benefited by making a call, and at the same time the entrepreneur also used to make some money out of establishing these PCOs. So similarly now the same entrepreneur can establish something called PDO, data office, where he can have a mechanism to resell the internet in the form of coupon, and also has a mechanism to connect to any available backhaul in the area, like a cellular backhaul, or a backhaul on fiber, or backhaul on fixed Wi-Fi. If nearby the backhaul is available, he can extend the backhaul on Wi-Fi. Similarly, he also require a computer or a computing platform to do multiple other activity. Like earlier we used to see in PCO, the person used to have a machine who used to generate the receipt of how much you have used and how much money you have to pay. Similarly, in this particular platform, the entrepreneur can generate vouchers which he can sell to an end user on 5 rupees, 10 rupees, 20 rupees, and allow them to access, let's suppose, 10 MB, 20 MB, 50 MB, 100 MB, as per the need of the end user. So, concept of PCO is similar to PCO. PDO is similar to PCO. It allows reselling of the internet bandwidth in the form of low denomination voucher, coupon to rural population to help them perform their immediate task. It allows a viable business model, because now the entrepreneur may be having already existing kirana shop, or maybe vegetable shop, or some other business going, and he has a footfall of people coming to his shop. So along with that, he can also sell the internet for the immediate task which people want to perform. So these are some of the boxes what we have deployed, which help achieve this particular requirement of reselling the internet. Some of the deployment which we have done in village, in VLE's house, where he just install the PDO and then connect to a nearby Wi-Fi hotspot as a fixed Wi-Fi connectivity, and start giving the internet voucher. Another work what we are doing right now is looking at our requirement, where more than 5,000 to 6,000 GPs which are not connected, and only possible solution is satellite backhaul. And as part of USOF and BBNL, already satellite bandwidth is getting deployed at more than 5,000 GPs to connect those villages. So after the satellite bandwidth is available in the area, the horizontal extension of that bandwidth to provide services in the form of voice, data, and video can be achieved through a solution which is satellite Wi-Fi. So we are taking satellite as a bandwidth, converting into our service switch, which efficiently use this satellite bandwidth to allow multiple simultaneous people accessing that bandwidth for the voice, data, or video requirement. So there are multiple bouquet of the product what we connect to the service switch. We connect Wi-Fi to cover the complete village and provide the connectivity. Or if an entrepreneur want to resell that bandwidth, there could be such mini PDO type of boxes through which he can generate the voucher and sell. Directly we can connect phone line on the service switch and create community calling facility, where people can make a VoIP call. So right now BSNL is already deploying a service called Wings. So Wings is a VoIP call where user gets a 10-digit number which is as good as any BSNL landline or mobile number through which he can make a call. So those numbers we are using so that user will be able to make voice call, connect to the national grid. As well as we also saw that in such villages there could be a clinic, or there could be a post office, or there could be a small such offices which may require a PABX type of facility. So we have connected single channel PABX where people can make a call among themselves on a Wi-Fi, as well as they will be able to connect to the national grid over a single channel ATL line. So this is a solution which we have deployed at around 4 locations in collaboration with BBNL and BSNL, trial in Northeast as well as in Nainital block in Uttarakhand. So these are the solutions where we are offering multiple services like chat, voice, PABX service, voice calling, internet access, and even emergency alert over this particular network on the end user devices. So this is suitable in an area where other type of backhaul is not possible and only satellite is a possible backhaul. And in fact, we have also tried using a given satellite uplink downlink bandwidth to push more number of VoIP call using MB type of codec mechanism, because in general our normal COTS phone, such type of codecs are not available, but utilizing a gateway in the network, we converted all the call into very low bandwidth data, so that satellite bandwidth which is available will be efficiently utilized for such type of communication. Because we have seen companies like Emersat and all providing phones which are very expensive, maybe in 50,000 to 1 lakh, and very specialized, used by field people or defense personnel. But that is not possible for any common man to use such phone. So we have used already existing devices like any low-cost smartphone and enable VoIP type of communication, but still able to achieve similar efficiency as any Emersat phone or other phone provides. So another work what we have done and we are doing is utilizing the third balloon as a floating platform to provide immediate connectivity in the villages. So this is the architecture which we have developed, where we have floated a third balloon around 50 to 70 meter height using hydrogen or helium as a gas, and connected a Wi-Fi hotspot in the platform, which will create a Wi-Fi coverage in the down area, and utilized on-ground Wi-Fi hotspot to create P2P link with the third platform, and then redistribute that link on a local Wi-Fi hotspot where a user will be able to make all type of voice, video, and data services. And the Tether platform is connected with fiber and the copper, these two cables below to the satellite to the backhaul. Like if you see, we have extended a connectivity from the BharatNet and given a connectivity to this Tether platform, a Wi-Fi access point hosted there, and then created around 500 meter radius of the coverage area, and used on-ground Wi-Fi terminal to first create P2MP type of connectivity, and then redistribute over the local Wi-Fi, so that user devices can meet the requirement of because these devices can only transmit with a reduced transmit power. So they directly connect to the local ground Wi-Fi hotspot, which in turn will communicate with the third platform, and the data passes to the backhaul of the BharatNet. So we have done a few trials in collaboration with IIT Bombay and then TIFR ballooning facility in Hyderabad. And we have also designed our own gondola, which will carry the sector antenna to provide 360-degree coverage, as well as host the access point And what we have tested is around 18 kg of the payload, and we have used around 20 cubic meter balloon so that it can lift this particular payload and provide the connectivity. Now, with these experiment, there is a new project which is launched by Department of Telecom called COBAL, that is Cell on Balloon. So this is the test bed which is initiated by DOT, where multiple type of cell, including Wi-Fi and 4G, is being tried out in AP and Telangana region to connect multiple cluster of the village on such balloon platform. And the platform will be a shared platform for any service provider to use that platform and provide services to the end user. So this is a very important activity which has initiated now, and anyone interested can participate and provide their solution. And this will be developed as a full-fledged test bed for such type of experiment. Another work what we have done is emergency alert over Wi-Fi, because this is also one of the requirement in rural area. And right now such emergency alerts are well defined in a cellular standard, where the mobile is capable of receiving such type of alerts, and user get informed that maybe the disaster is expected, heavy rain is expected, or wind is expected, or multiple other type of information which our NDMA or SDMA transmit. But Wi-Fi as a standard is not directly defined and designed for such type of communication. So CDOT has done certain work on how such information can be communicated to a user which is connected on a Wi-Fi hotspot. And recently we also got a patent on this particular architecture. And now we are working in IEEE 802.11 BC, that is Enhanced Broadcast Group, where we are looking to enable such type of emergency alert communication over public Wi-Fi network. Another testing what we are doing, and as Prasad also discussed in his presentation, is how to utilize wireless or microwave link in unlicensed band, that is 5 gigahertz band, for point-to-point and point-to multi-point requirement. So before 2018, the outdoor deployment for P2P type of requirement, only around 50 megahertz channel bandwidth was available in 5 gigahertz band earlier. But post 2018, government has opened around 605 total megahertz capacity in 5 gigahertz, in which around 250 megahertz can be utilized for point-to-point connectivity in first band and that fourth band of 5 gigahertz band. So there now we have 80 megahertz channel bandwidth as well as 160 megahertz channel bandwidth available to create such point-to-point connectivity. And then there providing high bandwidth point-to-point link is now possible, which was not possible earlier. So we have been doing certain work with respect to creating connecting the important institution in the GP, like school, hospital, village, or household, over 5 gigahertz point-to-point connectivity, where fiber pop from the ONT is terminated on Wi-Fi access point, and then these household, school, hospitals with line of sight, another CP equipments are connected on their house, where a direct point-to-point connectivity is established, and the data is now distributed inside the home in terms of Wi-Fi hotspot or copper cable. So this is one of the cost-effective mechanism to connect all these household, school, hospitals in rural area using 5 gigahertz point-to-multipoint band. Similarly, if we need to extend the connectivity, let's say up to 10 kilometer range, and if line of sight is available, same 5 gigahertz can be used in P2P connectivity, extending the connectivity from GP to the village level, and then provide the connectivity in form of Wi-Fi hotspot. Another one, mechanism which is being utilized in villages is once the fiber get terminated in the village GP, how to extend this particular fiber again to the nearby villages. So there is a unique proposition of using fiber ONT. That means the fiber ONT will have fiber as a termination, as well as again it will give fiber which can be extended to these all villages. This particular mechanism is being deployed by CSC, that is Common Service Center in GPs, where they tap the existing ONT, connect the copper cable from ONT to another OLT in the GP itself, and from the OLT again extend fiber to the home, because they have been told to provide one Wi-Fi hotspot and 5 FTTH connection in a GP. So what is being done is, again, the fiber from the BharatNet terminating on the ONT is tapped in another OLT, a local OLT, small OLT in the village, and from there it is again extended to the house in terms of FTTH. Similarly, if you want to connect the villages, which may be 2 to 3 or 4 kilometers away, the same fiber can be terminated on a fiber ONT, and from there fiber can be extended to these villages. And since fiber ONT is an active element, the losses will be reduced, and the bandwidth will be able to provide the bandwidth in the villages. With respect to HCI, as I mentioned earlier, that for the digitally illiterate people, it is very difficult to access the content in the same form what is available on internet today. So SCI primarily refers to how the content and applications are presented on the user device and how a user interact with it. So SCI must be built for illiterate or digitally disadvantaged people, mostly in rural area. Rather than text-based content, which is mostly in English, information is speech, images, or video, or combination through touch, speech, gesture, handwritten instruction on paper, pre-programmed card, simple gauge, etc. is required. So for example, if a villager wants to know a certain, maybe sugarcane price of the mandi today, he just need to have a card that is a pre-programmed card, which once he comes to the system, he just need to show that particular card, and automatically the system will retrieve the price of sugarcane and display that on the screen, which he can easily view and understand. He doesn't need to go to maybe Google or need to type or open the mandi website. So such type of intuitive human computer interface will really help those digitally illiterate people to adopt the technology, and that can innovate. There could be multiple innovation to help these people interact with the technology and achieve it. So we have designed a product called Gyan Setu, which actually has this interface, which has multiple SCI client, and backend there is our server. First of all, the interaction will happen with SCI server, which in turn will go to the internet, it retrieve the information and pass that information in a human readable form to the end user. So such type of systems need to be designed to really make it meaningful for the digitally illiterate people in the villages. Now, apart from that, now another major discussion what is going on, connecting 6,000 villages in India in 1,000 days. That is what the new discussion and the challenge what we have. And out of these 600,000 villages, already 250,000 villages are Gram Panchayat, which is already getting deployed by fiber or IP/MPLS technology. So we have done a study that how deploying in rest of villages, that is around 350,000 villages, how we can achieve the target of 1,000 days. So we have taken certain guiding principle during our discussion in a policy research group at NTI PRIT, where I'm also a member. So we have done multiple guiding principle we have taken, like readily available resource implementation time within 1,000 days, ease of implementation and availability of manpower locally to deploy such network, service model, sustainability model, that whenever the network is getting deployed, how it can be made sustainable, low power requirement, survey work and site selection in these villages, minimum coordination with state government and agencies can be envisaged to meet this 1,000 days target. Proven technology and availability of equipment. So this is one very important criteria, was that whatever technology we are proposing, whether it has been already proven in the field and whether the manufacturing base is already available in the country to meet such requirement, supply of such requirement in short time. Power supply space security at GP and villages is another criteria which we have looked at, where to keep the equipment so that it will not be stolen or it will be maintained properly. Also, we have looked into indigenous technology for Atmanirbhar Bharat, that what all technology has already can be indigenous, are already developed indigenously in the country. Country has the expertise of those technology. So with these guiding principle, we have done certain decision parameter analysis, and we have seen the distribution of the population in the villages. So we have found there are less than 200 people living into around 82,000 villages. 200 to 500, around 1,14,000 villages, such type of distribution which we have seen. And we found that around 2.6 lakh villages, more than 1,000 populations are already GP and already getting connected on fiber and IP/MPLS. There are around 1.97 lakh villages having less than 500 population, around 110 household, and there are around 1.42 lakh villages having population between 500 to 1,000. Is the distribution which we understood. Another thing also which we have seen is which are the villages, what are the distance between Gram Panchayat to villages less than 3 kilometer, 3 to 5 kilometer, and more than 5 kilometer. And apart from that, we have also seen a remote area, difficult area, and we have taken a minimum 100 Mbps drop in each village as one of the requirement. So with this decision parameter, and after discussing with multiple stakeholders, we tried to explore that it could be possible to meet requirement of connecting 600,000 villages if we explore the possibility of connecting villages more than 500 population till 1,000 population, around 1.41 lakh villages with the overhead fiber. As Prasad had told earlier, that the maintenance of these overhead fiber is one of the challenge. But fiber, why we have selected overhead fiber, because we see these villages, there is yet to have concrete road built. So if we will dig the path for the fiber, and when there is a road construction start, there will be a frequent fiber cuts. So overhead fiber will be better mechanism, which will also cost is also less to distribute. And distribution at the village could be on Wi-Fi hotspot or through fiber extension or copper cable extension. The population less than 500 and distance less than 3 kilometer, the 1.97 lakh villages, the proposal was to use a dedicated 80 megahertz bandwidth for in 5 gigahertz band for fixed Wi-Fi equipment to extend such connectivity. And then there are around 20,000 area which villages which is remote and hilly. So there could be multiple options, but the major predominant option is satellite as a connectivity in this particular area. So this is the three thing, like overhead fiber for 1.4 lakh villages and 5 gigahertz unlicensed band, which is low cost, and equipment base and manufacturing base is already available in country. So such type of equipment will meet a requirement of dropping 100 Mbps in these villages and satellite-based communication. So this is from my end with respect to rural communication, the Industry Connect program, what we are doing. Apart from that, what are the few solutions what we are working on to meet the requirement of rural communication, and the present discussion of how to connect 600,000 villages in country within 1,000 days. So thank you everyone.
The spectrum allocation, I think it is perhaps Sandeep is better to answer this.
So, with respect to spectrum allocation, uh, I think for the rural connectivity, of course, that sub gigahertz band is something which is very, very lucrative, and there is lots of discussion which took place during 5G high level forum, spectrum committee as well. So that is something which we can explore, because if we have such sub gigahertz band spectrum, then the reach can be increased. But only a concern would be the capacity, because now we are looking at high capacity requirement in the villages where maybe video content absorption is very high, or work from home, or I'll say uh, remote education is one of the main requirement in village areas. So otherwise, another thing what can be explored is 5G as a fixed wireless access, extending high bandwidth in maybe 28 gigahertz or other band in the village, and then distributing over Wi-Fi. So that could be also one of the very useful way of exploiting 5G for the rural connectivity. I'll add one more point with respect to 6G, that in fact there is already one closed group which is already being formed, where rural requirement to be discussed or taken for the 6G is already, people are already discussing. One of the things what we listen to multiple other folks who are researching is that for rural now, maybe the focus should shift towards a consistent connectivity rather than high bandwidth connectivity, because the rural the average internet bandwidth required to achieve multiple use cases will be low. But how that connectivity can be provided consistently, that is where now focus is moving, rather than just increasing capacity of the base station. Now the focus is also towards making consistent delivery of the bandwidth to the end user.
Just wanted to add, this is Alok here. I think the sub 6 gigahertz and 26, 28 gigahertz are being used for 5G globally. I'm saying, and India is also looking into that aspect. So moving forward, I think in 6G time frame, it is expected that 39 gigahertz onwards, these explorations, and you talked about 60 gigahertz, Prasad talked about 71, 81, 86 gigahertz. So these are being explored, and the right band among them would be chosen. This doesn't mean it will be only millimeter wave part of it, but like 6 gigahertz and below is in the 5G. Same way we expect there will be a relatively lower frequency that will also continue. So that's on the spectrum, and I think Sandeep very nicely highlighted on the point of consistent connectivity, not just the bandwidth. Thank you.
Okay. Uh, Sure, yes. So in all the slides that I had presented, I was talking about two parts: transport and distribution. Distribution being the access. So transport is always infrastructure oriented, which is like tower to tower, rooftop to rooftop, those kinds of architectures. So all of the fiber or the fixed wireless, the TV white space, or the even the V band, W band, all of them are entirely related to infrastructure oriented, tower to tower. So the access part is the last part that I had mentioned, which is related to either the pico cell, femto cell of 4G, 5G, or the wireless using 2.4, pi, or 60 gigahertz, or even the localized LAN kind of network. So those are the localized spaces which are finally reaching the end users' handsets or devices. So none of the other ones, which is primarily related to transport, directly reaching the end user. So hope that, or end users equipment. Hopefully that clarifies that. Yes. No, this is no, basically that was an internal study done at Astrom where we basically did the architecture of connecting between the devices. So that is not public domain data yet. Yes, yes, he can get in touch with me directly.
Yeah, just a related one. Sorry, Subhash, to interrupt you. In fact, there was a request to get the contact details of both speakers. Yeah, maybe you can mention that, or it is there in your slides. I think that will be good. They can contact you directly.
Yes, that will be great.
Yeah, that would be.
Thank you. So if let's say the spectrum issues are resolved for low bandwidth requirement, as Sandeep was mentioning in terms of consistent connectivity, not really bandwidth sense. I think TV space, TV white space, if the spectrum issues are resolved, will be a good candidate for it. But it will not be a good candidate for high bandwidth requirements. E-band is the right choice for high bandwidth requirements, and licensing regimes are also getting set in India, and globally also it is set in many countries. Yes, yes, it will be. So in the use case analysis, I had presented one slide there where I had compared the capex of different models, and you can see that the capex costs are very, very low in terms of realization if it is put in together. And that was the whole highlight of the entire discussion, where how do you make the whole deployment or the transport uh, most cost economical so that it can be delivered to the end user. So the delivery part ultimately will be involving the access, but it will be extremely localized. So the transport problem is the most dominant problem in that, and the ROI finally links directly to the capex that anybody puts into it. So that's why the capex is the most important driving factor to it. When it comes to the access products, whether it is a hotspot or whether it is the picocell, the typical ranges there that is targeted will be upper bounded by I think about a half kilometer, and maybe you can stretch it to a kilometer, but there will be less and less effective. But it is extremely suitable for a shorter range. For example, 200, 300 meters, it is ideal.
Yeah, so just to add to that, yeah, in the hotspot scenario, I think 500-meter max we will, stretch it. Only the limitation will come from the hand devices, which cannot transmit, has a limitation on the transmit power. But with point-to-point type of fixed connectivity, depend upon how much bandwidth drop what we require, but it can be extended to 3 to 5 to 7 kilometer easily. But yes, it comes at a cost of bandwidth. So right now, to increase the bandwidth, we are also looking to use Wi-Fi 6 as a technology to create point-to-point links so that capacity can be enhanced. So these are the two scenarios. One is in hotspot, one is in point-to-point link scenario.
Sandeep, sorry, Sandeep, I have a follow-up question on that one. If you are using Wi-Fi physical layer for the point-to-point or hotspot, you anyway you have a limitation coming from the SIFS time, 9 microsecond. You cannot go beyond 1.2 kilometers unless you go and modify the MAC for changing that SIFS time. Is that something CDOT did for the deployment in the rural area?
Yes, so exactly. So what we have done is modification on the MAC with respect to reducing the dependency on the ACK is where we have done the modification at the MAC layer, so that we are able to establish around 8.5 kilometer link, which was earlier in G. Now we are migrating it to 11 AC. And similarly, with Wi-Fi 6, right now we have done an experiment of around 300 to 350 meter, point-to-point link. But yes, that is what the MAC modification that is done to get away with the strict SIF requirement.
Okay, great, thank you.
Yeah, so I think we are really at a time where now I see LMLC is getting adopted as part of IMT 2020. So it is good to see when we will have that deployment in India, which will really solve a lot of requirement issues. And apart from that, the deployment of backhaul, middle mile, and access with technology like Wi-Fi, TV, white space, fixed Wi-Fi is something which will coexist. But it is really interesting to see when we have the LMLC deployment in India and see what is the performance it is able to provide to the end user. So it's an exciting time to see it will become reality in very soon, I understand.
So I just want to add one point there. See, ultimately any network deployment is a function of how much returns a particular operator can derive. One of the interesting things that has happened in the 5G domain is that the 5G has become a more what should I say, capable or amenable to house heterogeneous networks, where the network topology is flexible. What kind of backhaul, mid-haul, front haul, all of these splits that have come in the 5G is very critical for realizing different topologies and in a most cost-effective way. So that's why I believe that 5G adoption for rural is more, more possible and more realizable compared to 4G's adoption.
So I think what I can provide an answer right now with respect to BharatNet, uh, uh, the fiber, though it has a large capacity, but the drop what is being envisaged at every GP is not more than 100 Mbps. And at the block layer, the OLT has a capacity of maximum 2.5 Gbps as a drop, which is distributed in each GP at the ONT. Right now, what is actually available is around 10 Mbps in each GP. So I think I'm not sure whether I answered to that, but that is what is we have at BharatNet. But as and when the actual uplink can be increased, more drop is possible at each GP.
No, nothing specific. Thank you.
Yeah, just one more question we missed out. Just let me read out. Harshavardhana has asked, when will BSNL IP-based call connectivity be implemented?
So with IP-based call connectivity, as I told, BSNL has also deployed something called Wings as a service. So this is somewhere where user gets a 10-digit number, which is as good as a mobile and landline number. And that can be configured on some VoIP software which BSNL has recommended, and can take a service as a normal IP telephony. That is already available.
Okay, I think that's the last question. So with that, it's my duty to do vote of thanks. I would like to first of all thank the speakers, Dr. Prasad and Sandeep. And I really enjoyed both talks, like both gave a different viewpoint for the rural communication. As a slight deviation from the conventional vote of thanks, I want to just give a very quick summary of what the speakers covered. I think Dr. Prasad started with how the rural area and urban area, the ratio proportion is and the population proportion is. And he covered various technologies covering from the TV white space to all the way to V-band, E-band, and even the IR, FSO, free space optical communication transport mechanism. And he also covered about the access, various access technologies using picocell, femtocell, or Wi-Fi, or even the wireless LAN, 802.3.LAN. And interesting experiments what they conducted in the near Mysore, covering about 3 GPs. And he also touched upon about the gigamesh and the satellite communication technologies, what they are working on. And Sandeep covered the Wi-Fi rural communication and also mainly the standard activity and the industry connect. I think he gave great deal of details on that one. And what they are doing in P2872 and P2061, mainly covering the interoperable and secure Wi-Fi communication and frugal 5G. And he also explained the rural connectivity program, what CDOT has been doing it for several years in connecting the rural area. Luckily, I was involved in both these projects in the early stages. So I can really see the improvement in the quality and the product placement in leaps and bounds. So I would like to congratulate both of you on the product deployment, what you have done. And now we're coming back to my regular vote of thanks. I would like to thank the speakers and of course the organizers, Chengappa and Subhas has done a lot of work behind the screen. And of course the ComSoc team, entire ComSoc team was spearheading this whole arrangement of the workshop. And last but not the least, all the attendees and very active and asking questions. I would like to thank all of you to attend this on a Saturday morning. And I'm looking forward all of you in the future workshops. And before I leave, please fill the feedback form. So that will give us information about what can be done in the future workshops. Thanks one and all.
Thank you. Thank you.
Thank you.
Thank you. Bye.